So in this video, we're going to follow on from our previous tutorial and we're going to derive the response of the pendulum with respect to time from this differential equation that we previously obtained. So before we do that, let's just have a look at the differential equation and let's note some facts about it. So the first thing about this differential equation is that it's linear. And what that effectively means is that there's no sine theta terms, there's no tan theta terms, there's no theta cubed or theta squared terms. Theta is expressed on its own and multiplied by a constant coefficient. So in this case, the second derivative of theta, its coefficient is just 1. In addition to this, the differential equation is also homogeneous, which essentially means you've got a 0 term over here on the right-hand side. Also, the differential equation is ordinary. And that means that theta and its derivatives are dependent upon only one independent variable. And that independent variable is time. So effectively, theta is a function of time. Now, calculus courses deal extensively with this type of differential equation, and they're normally quite straightforward to solve. But for our purposes, we're going to just try and understand what the differential equation is asking. So effectively, what this differential equation is asking is it's looking for a function of time that when I derive it twice yields a constant multiplied by that function of time again. So effectively, I'm looking for a function that satisfies this. And an example of a function that actually satisfies this criteria is sine omega t. So for example, let's take a look at sine. Let's let sine equal to f of t. And therefore, the second derivative of sine omega t is minus omega squared sine omega t, which is just a constant multiplied by sine omega t. And since sine omega t is our function, it's just af of t. Now, sine is normally, this is a special case of sine, where the amplitude A is 1 and the phase phi is 0. But sine is normally written in its more general form as f of t in this case is a sine omega nt plus phi, where a is the amplitude, phi is the phase, and omega n is the natural frequency. Now, what this effectively means for our pendulum example is if I draw the pendulum deflected by an arbitrary amount to the right, and let's say that's the state of the pendulum at time t is equal to 0, so we'll call that t naught. As we know, the pendulum is going to oscillate, and it's going to go from here over to here, eventually, and then backwards and forwards again. And we're assuming no damping in this system, so it's going to do that for the rest of time. If I draw out the position of the pendulum on a set of axes here, so we'll label this set of axes as t for time, and we'll label this set of axes as theta, where theta is the angle of deflection. If this is the state of the pendulum at t is equal to 0, or at time is equal to 0, then our response should look something like this. Now, this value here is our amplitude. And that is this distance in here. This distance here, approximately, would be our period, t. And if I just redraw these axes horizontally, say this is our response for our particular example. And let's say this is an ordinary sinusoidal function with no phase. This distance in here will be our phase. And one way to spot the phase is the sinusoidal functions aren't overlapping anymore. One is lagging and one is leading. So with that in mind, it is also worth mentioning that phi and A, which are our phase and our amplitude, are dependent on the initial conditions of the system. Now, for a second order differential equation, two initial conditions are required to solve for the response of the system. And we'll call those initial conditions theta naught for the initial angular position of the pendulum and omega naught for the initial angular velocity of the pendulum. So now we know that we have three unknowns. Those being A, phi, and omega n. And we have three equations. So we can solve for each one of those unknowns. So now let's take a look at the first equation that we're going to use to solve for our unknowns. And that's just the equation of motion of the pendulum, which is the double derivative of theta plus g over L times theta is equal to 0. And we also know now that theta is a function of time and is equal to a sine omega nt plus phi. Now what we're going to do is we're going to obtain the double derivative of this function, and that's going to leave us with the double derivative of theta is equal to minus omega n squared a sine omega nt plus phi. And if we sub both of these expressions into our equation of motion, we end up with minus omega n squared a times sine of omega nt plus phi plus g over L a sine omega nt plus phi. And that is all equal to 0. Now what you'll see is that both of these terms have an a sine omega nt plus phi. And if we divide both the left-hand side of the equation and the right-hand side of the equation by a sine omega nt plus phi, we end up with minus omega n squared plus g of L is equal to 0. And therefore, omega n is equal to plus the square root of g over L. Now what's important to note is we're only taking the positive square root, as a negative frequency doesn't make much sense given the context of this problem. Now this relationship tells us something important, and it tells us that when we increase the length of the string that connects the ball to the ceiling, the angular velocity of the pendulum will actually decrease. And if we decrease the length of the string, the angular velocity increases. So it's an important relationship. So now let's take a look at the two other equations needed to solve for our unknowns. And the first thing we know is that theta at time t is equal to 0 is equal to our initial displacement of the pendulum. And the second thing we know is that the derivative of theta at time t is equal to 0 is equal to our angular velocity, or omega naught, or equal to our initial angular velocity, omega naught. So we also know that theta is equal to a sine omega nt plus phi. And with that, we know that theta at time t is equal to 0 is equal to a sine omega n times 0 plus phi. And that is just equal to a sine of phi, which is again equal to theta naught. Now, the derivative of theta with respect to time is going to be omega n a cosine omega nt plus phi. Time t is equal to 0, that derivative is equal to omega n a cosine of phi. And that expression is equal to our initial angular velocity of the pendulum. So here we have two equations, and you'll notice that both equations contain two of our unknowns. So they need to be solved simultaneously. So we have a set of simultaneous equations. And the first thing we're going to do is we're going to solve for phi. That's probably the most difficult thing to solve for in this derivation. So to do that, we're going to divide equation 1 by equation 2. And that leaves us with a sine phi over omega n, a cosine of phi, is equal to theta naught over omega naught. And sine phi over cos phi is just tan of phi, and the a's also cancel. So what that leaves us with is 1 over omega n multiplied by tan of phi is equal to theta naught over omega n, or over omega naught. We can bring the omega n over to the right hand side by multiplying both sides by omega n. And that leaves us with tan of phi is equal to theta naught over omega naught times by omega n. And to obtain phi on its own, we just get the tan inverse of both sides. And that leaves us with phi is equal to tan inverse theta naught over omega naught times omega n. Now, unfortunately, it's not just as simple as using this equation here to calculate out phi. We need to understand what quadrant the phase is in. And the way that we do that is we're going to draw out the different quadrants that our phase can be in. So we'll draw two axes. We'll label this axis here as omega naught over omega n. And we'll say this is the positive side of the axis, and that's the negative. And we'll label this axis as our initial displacement, theta naught, and we'll label this as the positive side of the axis, and this is the negative. So we've three quadrants: 1, 2, 3, 4. Now let's take a look at the first quadrant. Our phase will be in the first quadrant when theta naught is positive and omega naught over omega n is positive. So effectively what we've done is, if you can imagine our pendulum at its neutral state, we've deflected our pendulum over by a certain amount. We'll call that theta naught. And it also has a velocity acting in the same direction with a magnitude of omega naught. And by using this equation, we're effectively calculating this angle in here. So for the first quadrant, that's phi. But in the second quadrant, theta naught is still positive, but omega naught over omega n is now negative. So effectively what ends up happening is, although the initial displacement was positive, the initial velocity is actually negative. So omega naught is going in that direction. And if we were to apply the same equation to calculate for a phase that's in the second quadrant, we'd end up with this angle in here. But the phase is actually measured counterclockwise from this line. So we need to take into account the quadrant that our phase is in. Now, the easiest way of doing this is just to consider each phase individually and derive an equation that can be used to calculate out the phase in that quadrant. So let's start out with quadrant 1. For quadrant 1, theta naught is positive, and omega naught over omega n is also positive. So phi is just tan inverse theta naught times omega n over omega naught. Now for the second quadrant, theta naught is still positive, but omega naught over omega n is now negative. Which means that to calculate out phi, it's pi minus tan inverse, and it's the absolute value of what's inside the tan. I would use the absolute value just to save you from going wrong. For the third quadrant, theta naught is now negative, and omega naught over omega n is also negative, which means to calculate out our phase, it's just going to be pi plus tan inverse and the absolute value of what's in those brackets. And lastly, for the fourth quadrant, theta naught is negative, but omega naught over omega n is positive. So phi is 2 pi minus tan inverse theta naught omega n over omega naught. And these four equations can be used to easily calculate the phase for every pair or every different pair of initial conditions in the system. So now we're going to take a look at deriving an equation for the amplitude of the response. And to do that, we're going to use the two equations that we derived earlier. And these equations are a sine phi is equal to theta naught, and omega n, a cosine of phi, is equal to omega naught. Now, we're going to square the left-hand side and the right-hand side of both these equations, and it might not seem obvious why we're doing that, but it will become clearer as we go through. So let's take the first equation. That's just going to become a squared sine squared theta is equal to theta naught squared. And to clean that up a little bit, we're just going to divide both sides by a squared. So that's going to become sine squared of phi is equal to theta naught squared over a squared. And for the second equation, it's going to become omega n squared, a squared, cosine squared of phi is equal to omega naught squared. And again, to clean it up, we're going to divide both sides by omega n squared a squared. So we're left with cosine squared of phi is equal to omega naught squared over omega n squared a squared. Now, we're going to add both of these equations together. And that means that the equation now becomes sine squared phi plus cosine squared of phi is equal to theta naught squared over a squared plus omega naught squared over omega n squared a squared. We know from trigonometry that this expression is just equal to 1. So effectively what we end up with is 1 is equal to theta naught squared over a squared plus omega naught squared over omega n squared a squared. And then we multiply both sides by a squared. And we end up with theta naught squared plus omega naught squared over omega n squared. Now, that means that we can take the square root of both sides and we get a is equal to the square root of theta naught squared plus omega naught squared over omega n squared, which is the same thing as saying theta naught squared omega n squared plus omega naught squared, all under a square root, divide by omega n. So now we've obtained a function that allows us to calculate the amplitude of the response based upon the natural frequency and the initial conditions. So now all that's left is to put all of this together and obtain the overall response to the system. So if you'll remember, theta t is equal to a sine omega nt plus phi, and knowing that omega n is equal to the square root of g over L, and that phi is tan inverse theta naught omega n over omega naught, we can put all this together and we obtain that theta t is equal to the square root of theta naught squared omega n squared plus omega naught squared all over omega n multiplied by the sine of square root g over L times t plus the tan inverse theta naught times omega n over omega naught. And that is the response of the pendulum against time. And it's dependent upon the initial displacement, the initial angular velocity, and the natural frequency, which is just square root g over L. And a final word of caution is to be careful of the phase. Of phase.